Yep, so today's AI is built upon this math theorem called the universal approximation theorem, which basically says that a high-dimensional function is a linear combination of random features of some nonlinear function, sigma. So this is equivalent to a neural network. Today it's known as the multi-layer perceptron. So are there any alternatives? Are there any alternative math foundation? And correspondingly, we can build another AI skyscraper based on this new math foundation. And the answer is yes, we can. And that theorem is called Kolmogorov-Arnold representation theorem. And we'll see how we can use this as a building block to build another AI world. So here's the KA representation theorem, or short as CART. Don't worry about this complicated formula. Basically, this formula tells us you can decompose a high-dimensional function into a bunch of 1D functions plus summing. So this is like extreme great news for approximating high-dimensional functions, hence machine learning, because machine learning data sets are usually very high-dimensional. You can basically decompose something complicated into something simple. So that gives us a lot of promise. Immediately, here's a plot twist. Back in 1989, Professor Poggio and collaborators, they wrote in a paper, said that we review Kolmogorov's theorem and show that it is irrelevant in the context of networks learning. So that basically sentenced the theorem to death. For years, in the context of machine learning, that's like the final nail in the coffin, end of the story, and that's the end of my talk. Thank you very much. So I'm just kidding. So let's take a look why they say the theorem is irrelevant. So the key here is that they allow the 1D functions to be continuous, but not necessarily smooth. But in practice, what we care about and what's practically learnable are only smooth functions. Although their argument is mathematically sound, I'm trained as a physicist. Also, Max was trained as a physicist. So our level of rigor is lower than mathematicians. So we were more naively optimistic about the usage of this theorem. So firstly, empirically, maybe we don't care about exact representations. Approximate ones may suffice in practice. Secondly, a common wisdom of modern deep learning is going deeper. Even under the smooth constraint, deeper nets can be more expressive, and that might be enough. And lastly, the can-do spirit. Let's just do it and see how it works. Cans may not work in the worst cases, but may work for typical cases, and that might be enough. So with the can-do spirit, we extend the original representation theorem and propose this new architecture called CAN, Kolmogorov-Arnold Networks. A CAN is nothing but just a parameterization of the representation. But what's more, but beyond that, we notice that the original representation is just a two-layer network from which we can easily define the so-called CAN layer. And this network is basically a stack of two CAN layers. By defining the CAN layer as the basic building block, we can make the network deeper and deeper. That is the original two-layer. You can easily stack 3-layer, 4-layer, 5-layer, as deep as you want. Now, so what? So we have CANs. Firstly, CANs are accurate with faster scaling laws. We care about scaling laws in large models because the scaling laws give us the promise how much performance improvement you would get from scaling up your model, data, or compute. And CANs are particularly promising because it tells us how to decompose a high-dimensional functions, again, into 1D functions. So your scaling law is as good as approximating 1D functions, which we know mathematically how to approximate these 1D functions. So with that, we can largely improve the scaling exponent from proportional to 1/d, which suffers from curse of dimensionality, to something that is independent of your input dimensionality. the dimensionality is always 1 because of the representation theorem. And based on some simple examples, we show that we can indeed empirically with CAN to achieve this theoretically scaling. But again, the caveat is that calling back to the 1989 paper, we may not always have the exact representations, but sometimes we only have approximate representations, but that's still promising. But still, the decomposition idea is still promising, like how you decompose a high-dimensional thing into low-dimensional thing, and you deal with that in the low-dimensional space. Besides being accurate, CANs can also be interpretable. You can train the CAN, you can sparsify it, you can prune it, you can symbolify it, all the way down to symbolic formulas. Although Max is not here, let's imagine that there is this fictional conversation between my advisor Max and the CAN. So here, CAN is like a trisolarium from the three-body problem, or in Chinese, Santi. So these trisolarians, or Santiren, their brains are totally transparent, so they cannot hide any secret from others, from human beings. So Max just went up and asked, here's my data set. Well, Max doesn't sound like this, but just to make the distinction. So Max went up and said, here's my data set. It contains the mystery of the universe. And the CAN went, I'm ready, Max. Here's my brain. And Max like, great, train your brain. Done. It looks like there's some redundancies in it. Prune it. Done. Can you further symbolify it? Yes, I can. So from this massive data set, massive network, it simplifies all the way down to symbolic formulas, this symbolic formula, which is completely interpretable. But let's imagine another conversation Max would have with MLPs instead. Max went up and said, here's my data set. It contains the mystery of our universe. And MLP went, I'm ready, Max. Here's my brain. Great. Train your brain. Done. Did you really train it? It looks as messy as before. But MLP went, I really trained it. The loss is pretty low. It's just the connections are really complicated. So now Max got confused. What's going on? So MLP went like, you stupid humans can just not understand the way I do the computation. So from a philosophical aspect, there's a distinction between CAN and MLP. CANs is like clockwork. PCs are customized, like you have those learnable activations, and those PCs have clear purposes. It's easy to tear them apart and reassemble. By contrast, MLP is like house made of bricks. PCs bricks are produced in a standard simple way. It's difficult to, once you build a house, it's difficult to tear them apart and then reassemble. So in CANs, parts are complex, combinations are simple, which is aligned with the philosophy of reductionism, or some kind of symbolism. And for MLPs, parts are simple, combinations are complex, which is aligned with the philosophy of holism, or what we know as connectionism. So the complexity of CANs coming from the complexity of individual parts, but they are nevertheless interpretable because they have clear purposes. However, for MLPs, the complexity coming from the connecting patterns, which are, in some sense, by definition, not that interpretable to human beings. So given the good properties of CANs, what's next? So for me, I would love to see, we can use interpretable AI tools, apply it to attack fundamental science problems like high TC, superconducting, nuclear fusion, millennium problems. But CANs also have the potential to solve real-life applications like language vision models, weather forecasting, healthcare. So with that, I'm looking forward to a bright future full of many new scientific discoveries enabled by interpretable AI, and I hope that we can contribute to that future together. Thank you so much for your attention.